Hello everyone. So in this tutorial we will look at practice question number 8 and practice question number 9 of week 10, which is basically based upon the timestamp ordering protocol of concurrency control. Um, so let's start it. So what is question 8 asking? It is saying that there is a given schedule S, and if the timestamp for transactions T1, T2 and T3 are respectively 25 and 10, then choose all the correct options. So here I have drawn the tabular form of the schedule, and it is given that the timestamp of T1 is 20, for T2 is 5 and T3 is 10. That means T2, which has the minimum value of timestamp, that transaction is the earliest or is the oldest transaction among the three, followed by T3 whose timestamp is 10, and then at last the newest transaction is T1 whose timestamp is 20. So we know according to the timestamp ordering protocol, the minimum value of the timestamp is given to the transaction who has arrived earliest, or basically which is the oldest one among the three. So when I say oldest or youngest, what that means is that in the I mean while processing the transactions, right, T2 has arrived at first. Now that doesn't mean that T2 will be executed completely before executing T1 and T3, as we know that we are dealing with a interleaved concurrent systems in database engine. So it might so happen that although T2 came first, due to interleaving of instruction, T1 and T3 some instruction might be executed, and not only might be, it will be executed at before completing all the instructions of T2 because of concurrency. So as we know, because of this concurrency only, we get problems with consistency. So we try to extract performance, but in order to do that, we do interleaving of instruction. And while we do interleaving, we run into inconsistent states. And in order to reduce these inconsistencies, in order to eliminate these inconsistencies, we came up with the notion of serializability, that although I am doing interleaving, although I am running concurrent schedule, the ultimate end result of running them concurrently should still be same as that of a serial schedule. So that concept is what serializability is. Serializability talks about, and within serializability we have seen notions of conflict and view serializability. Now times how now okay, I understood that okay, some schedules are serializable, and if it is a serializable schedule, then basically its result will be similar to that of a serial schedule, and even while I am doing interleaving. But how can we achieve serializability? This is a conceptual thing, but how can I practically implement serializability? The answer to that is different concurrency control protocol, which is locking, partial ordering protocol, and timestamp ordering protocol. So which are partial ordering protocol is kind of a graph based protocol, but anyways there are many other such protocols as well which we follow, whose main aim is to implement the concept of serializability. So timestamp ordering protocol is one such protocol which implements the concept of serializability in practice. Okay, just like locking, but locking has its disadvantages, and timestamp ordering protocol actually eliminates those disadvantages. So we know that even when the best locking protocols like rigorous or strict locking were used, still we couldn't get out of the problem of deadlock. Deadlock was still possible even in strict locking protocol, right? So that's why we came up with a different algorithm or different way of solving this issue, which is timestamp ordering. So that was a brief intro to why timestamp ordering is needed, and its main advantages: it does not run into deadlock, and actually it is rather easy to implement than locks, and that's why its real life performance is also somewhat better. But in some situations, timestamp ordering protocol may prove worse than locking protocol, and we will get to know that a little bit. But so now let's start the solution. Uh, so basically, what timestamp ordering protocol says is, with every data item, I will have two associated timestamps, right? For every data item, solution for every data item two timestamps will be maintained. One is the read timestamp, another is the write timestamp. So read TS and write TS. So since in this example we are dealing with the data items A, B and C, so read TS of A, write TS of A, right? Uh, I'm writing in short, read TS of B, write TS of B and read TS of C, write TS of C. So timestamp ordering protocol says that we will have these read and write timestamps of each of the data item, and we will have a timestamp given to each of the transactions as well. So in this case, transaction T1's timestamp is 20, right? I'm writing timestamp equal to 20. Here timestamp T2's timestamp is 5 and T3's timestamp is 10, right? Fine. Now, what does timestamp ordering protocol says that I will go on executing the instructions in the schedule, and every time I execute a read or a write on a particular data item, I will accordingly update the read timestamp and write timestamp of the data item with the timestamp value of the transaction which is updating or reading it. So let's say transaction T3 writes on variable A at some point of time. So I will immediately write, I will set the write timestamp of A with the value of the timestamp of T3, which is 10 in this case. So in that case, I will write 10 over here, right? So this is basically the idea of timestamp ordering protocol. So we will define the serializability concept by timestamp ordering protocol by the following rules. Yeah. So according to the timestamp ordering protocol, whenever a write operation is requested by a transaction, so basically whenever we are going to perform a write operation in the schedule, at first before performing that write operation, we will have to check that whether that write operation is valid, according to the rules of timestamp ordering protocol. So how will we check the validity of a particular write operation? For write operation, check both read and write timestamps of the data item, right? So we will basically check both the read and write timestamp of the particular data item on which a new write operation is being issued by a transaction. And how do we check the validity? The validity is we will only allow the write operation to be executed according to timestamp ordering protocol when the timestamp of the transaction which is going for the write operation, right, that timestamp is greater in value than the read and write timestamp of the data item. So what I mean is that a newer transaction, the transaction which is requesting to write on that particular data item is a newer transaction, is a younger transaction with a much bigger timestamp value than those transactions which have already read and wrote on the data item A. On the data item under consideration, right? So that is the rule. And for read operations validity, we will only check only the write timestamp. Right. So this is intuitive because while I'm reading something, I'm not worried about who else has read at what point of time, right? So I'm not worried about that. I am reading something. The only thing that is required to be kept in mind is there some other transaction which is basically younger than me and who has already written into that data item. Right. So when I'm trying to execute a read operation, I need to be careful about whether due to interleaving some younger transaction has come and it has already written into the data item. If some younger transaction whose timestamp value is more, they have come and already written into the data item in the past, then I currently being a older transaction with a lesser timestamp value should not go and read the data item because I should have read it earlier before the younger transaction came and updated it because he is younger. He should, I mean, before he executed his write, I should have read whatever I needed to read from the data item, right? Because I am older, so I should have done that earlier. But I didn't do it because of the interleaving or concurrency, and that's why I cannot do the read operation now, being an older transaction. So I must roll back. I will not allow the read operation. This is the basic idea. So both write and read operations are checked by, validity of the read and write operation before executing it is checked by looking at the read and write timestamp of the data item. And we will allow any younger transaction to do the read write afterwards in time, but if any older transaction comes and try to read and write it, then we have to apply the rules and check whether it is valid or not. So anyways, so we have discussed these two things. Now we will apply these two rules in our schedule and try to solve it. One important point is we will always, let me write it over here, another important point. We will always maintain the value in this read timestamp and write timestamp with the most younger transaction who has written or read from the data items, right? So let's say at some point of time I put the let's say read timestamp of B is 10, right? I'm not saying that it is according to the schedule, I'm just giving an example. So let's say read timestamp is 10 at some point of time, but later let's say another transaction comes and it requests for reading the value of B, right? And the newer transaction which has come and tries to read the value of B, let's say its timestamp value is 5, right? So a new transaction has a transaction has issued a read operation. Now I am checking the validity. In validity checking, I am referring the read timestamp of B and I see that the read timestamp is 10, but the transaction which has issued the current read, that's value of timestamp is 5. So that means it is an older transaction. Now we know that in this case RTS, we don't have to refer to the read timestamp, we have to refer to the write timestamp, right? Whenever any read is issued, like here, we only check the write timestamp. So suppose the write timestamp of B in this case is someone who is older than 5. So let's say 2, right? Write timestamp of B is 2. And the current transaction who has issued the read, that transaction's timestamp is 5. So we will refer to the write timestamp and we will see that the write timestamp of B is 2. Correct? So since the write timestamp is 2, it is a older transaction than it's a older transaction than me, and me being, the current transaction that I'm talking about, that transaction's timestamp is basically 5. So basically this means that the B was written by some older transaction, and if I'm trying to read the value of B now, then it is not an issue now because I'm a younger one. So then obviously the read will be allowed and this transaction will do the read. But now the point is B was already at some point of time in the passed was already read by another transaction whose value was 10. Correct. And now most recently B is read by another transaction whose value is 5. Okay. And if now should I update the RTS read timestamp of B to 5, because most recently B is being read by the 5 transaction with timestamp order 5, right? So should I update it? No, we will not update the read timestamp of B. We will keep it as the value which is the greatest value, in order to reflect the fact the most youngest transaction till now, from the start of the schedule till now, which is the most youngest transaction which has read the value of B or value of any data item. So we will not update it in this situation. Okay. So it will be kept at 10 only. We will not update it with 5. So this is another rule, just for an example. Sorry. Fine. So now let's, I'm not writing it. I hope I communicated the fact. Now we will go to the schedule. All these rules which we are talking, these are properly formally mentioned in the lecture slides. You can refer to them, but I feel that this is the basic idea. I mean, the ideas behind these rules are these things, that I will not allow any newer transaction to actually, sorry, any older transaction to write when some newer transaction has already written or read from it, right? That is the fundamental rule. Okay, so now we will apply the timestamp ordering values, and let us see what happens, whether this schedule is whether timestamp ordering protocol allows this schedule or not. So first we will see that WA is there, right? And T2 is issuing WA. It is the first operation, so nothing to worry. And we know that whenever we write according to the rule, this write operation, check both read and write timestamp. So I have to check both read and write timestamp of a variable, a data item, but it is empty, so we will allow the operation anyways. And we will update that the last write timestamp of a would be 5, right? So this transaction is allowed, no problem. Sorry, this instruction is allowed, no problem, and I will update the write timestamp to be 5. Next, the read operation is there. We know in case of read operation, we refer to only the write timestamp of that variable, of the data item. So here is the write timestamp of data item, which is 5. So that's not an issue, because 5 is a transaction which is older, and that means that A is being written by a transaction which is older, and I being T1, I being 20 timestamp transaction. So that means I am a younger transaction. So being a younger transaction, I'm going to read from the data item A, which was written by an older transaction. So that is what it is natural, right? Older transaction has written. Now I being new, I have come in presently and I'm trying to read it. So no problem. So we will allow the read. So this read is also allowed, right? And we will update the read timestamp of A to be 20. Fine. Next, this read by T3. Again, we will only refer the write timestamp of A. Write timestamp of A is 5, and here T3's timestamp is 10. So due to similar reasons, we will also allow this. Okay. Now, since I have read the value of A over here by this T3 whose timestamp value is 10, should I update the read timestamp of A to 10? No, right? We discussed the same point earlier, that we will only keep the value which is of the youngest timestamp, youngest transaction which has read the value or written the value from the start of the schedule to the current point of time. So we will not modify 20 to 10 here. We will keep it as 20, because 10 is a smaller value than 20. If this T3's timestamp would have been 30, then we would have updated it. Fine. So next is WA. Now we come to WA. Now this is a write operation. This is a write operation, we will have to refer to both read and write timestamp. So let's at first check the write timestamp of A. Write timestamp of A is saying 5. So again, no problem, because 5 is an older transaction and T1 being a younger transaction is going to write into A, and initially A was written by some transaction whose value was 5, which is basically transaction 2, so it is fine. I am a newer transaction, I can write over an older transaction. So no issues over here. Let's check the read timestamp. So read timestamp saying it is 20. So that means I have myself read the value of A earlier. So again, there is no issue with it. So we will allow write A also. And since now I have written into A, and I will update this write timestamp of A, here we will update. Why here we will update? Because here 5 was stored and now currently it will be 20, right? Now 20 being a younger, I mean T1 being a younger transaction with a greater timestamp value, we said that we will always try to reflect the youngest transaction, or in other words, the maximum value of the timestamp within this read and write timestamp of data item. So we will modify this 5 to 20. Okay. Uh, so WA is also allowed. Now we convert this WA of T3. Same, apply the same check on both read and write, because we are going for a write operation. So both timestamps needs to be checked. So let's check the write timestamp. Both of them read and write at 20. Now T3 has a timestamp value of 10. Now what does this mean? That a transaction whose timestamp was 20 has already read and written into the variable A. Now I being T3, a transaction with timestamp value 10, who is an older transaction, has come now to to write into it. So I am an older transaction. I should have written into it earlier, and then only the T1 transaction should have read from that value, because I am an older transaction. According to the serial logic, I should have executed my operations first, right? But due to interleaving for gaining concurrency, the T1 transaction, which is a younger one, which should have come later, has already read the value, right? So that's why this is not a valid situation, and therefore I will not allow this transaction. Timestamp ordering protocol will not allow this write to be executed, and it will simply roll back. I mean, right? It will go back to the, it will cancel the transaction T3. All the instructions within transaction T3 will be cancelled, and it will be rolled back to the start, and then again it will start with a new timestamp value, and then it will be executed again. So that means that this schedule is not allowed by the timestamp ordering protocol, and therefore the timestamp ordering protocol does not allow this transaction. Not transaction, it should be schedule. Does not allow the, not okay, no, that's correct actually. That does not allow the transaction only, because T3 is the transaction which is not allowed to proceed. So yeah, this is correct, and this transaction is basically T3. So out of these three, T3 will not be allowed, and it will be rolled back, and then again it will start with a new timestamp value, because it becomes a new transaction when it starts from, it's like a rebirth, it will start newly, and then we will see that the ordering is working. Fine. So now the next option is asking timestamp ordering with Thomas Wright rule allows the transaction. So what is this Thomas Wright rule? Thomas Wright rule is uh, Thomas Wright rule says that we will allow the delayed writes, not allow, ignore the delayed writes without without aborting or rollbacking, without aborting the whole transaction. So what does this mean? That some writes which are delayed means, as we have seen, like in this example, that the write of T3 is happening, T3 being an older transaction, still its write is happening later, and before this write is executed, the younger transaction T1 has already read and written into it. So that is a delayed write. So T3's write means it was a delayed write. So it says, Thomas Wright rule says that ignore the delayed writes. I mean, I will not roll back because of this delayed write. I will ignore, just ignore that. I will not execute it. That write will simply be not executed. It will be ignored, and then we will proceed with the other instruction within T3 transaction. Right? So we will proceed with the transaction. We will not roll back or abort, but we will ignore that particular write. Now, obviously, we must have to think that by ignoring this, I mean, we might run into some trouble, right? There may be some inconsistency or something like that. Yeah. So the rule caters to that part also, and it says that you can only do this when some younger transaction might have written into the data item which you are trying to write, but must not have read that data item. Okay, so the very most important point of this Thomas Wright rule is very important, that can only do this, can only ignore when the concerned data item is not read by any younger transaction, but might have written into it. Got the point? So I might have read, I mean, some younger transaction might have written into it, but no younger transaction has read the value, because see, it is quite intuitive. If someone has read the value, then it will reflect the changes within the database state. But if it is not read, only it is being written, and then I am kind of doing a blind, I mean, I am ignoring this write, right? I mean, the third, the delayed write, I am kind of ignoring it, so it will not make any changes into it. But if I ignore the delayed write when it has already been read by some other younger transaction, then the thing is not correct. Why? Because ideally, since this transaction, which is basically, I mean, the concerned transaction, right, which we are questioning whether to abort or not abort by Thomas Wright rule. So that transaction, that is the older transaction, since it is older, it should have executed at first completely, and then the newer or younger transaction should have come and read or written into it. So that means, according to the serial execution basic logic, and since we are basically trying to do serializability, so we will try to put the end result as the same as a serial schedule. So since an older transaction so the basic idea is the older transaction should have written, and then the newer transaction should have come and read from it. But therefore, if there is a read statement in the schedule, right, done by a younger transaction, then I cannot just simply ignore the delayed writes, right? Because that write should have come earlier into time, and the data written by that write should have been read by this younger transaction. But when no one has read it, only written into it, then that write doesn't make any sense. If there is a delayed write, what I can do is I can simply ignore the write, and then I can go forward with it. Right. So that is what Thomas Wright rule says. It's just a beautiful observation, and which will reduce the rollback, and which will increase the concurrency of the system. Right. It's just a nice observation that this rule states that no need to do the rollback when there is no read. But as we can see in this schedule, the read A is there, which is done by timestamp 20 transaction T1, and that's why we can see that RTS is 20 already, and that's why we cannot apply the Thomas Wright rule here, because Thomas Wright rule will not allow this thing when already someone has read it, right? If this 20 write TS was only 20 and this read TS was not 20, right, then we would have simply ignored this WA, we would have ignored this WA, and we would have moved forward with the transaction. There are no other instruction here, but let's say there were some instruction, then we would have moved forward. We would not have rolled back. Okay, we would not have rolled back, we would have moved forward. But that is not the case here, because again read timestamp is 20 as well along with write timestamp. So simply to say this, what do I mean is, if read timestamp is basically smaller than the current transaction in question, current transactions timestamp, and write timestamp is greater than current transactions timestamp, then Thomas Wright rule, ignore the write and proceed. Right? So this is what Thomas Wright rule says in summary. But this is not the case, because this RTS must be lesser than current timestamp, it should be there. But this is not happening in this case, because RTX is 20 here and the current timestamp is 10. So Thomas Wright rule also will not allow this schedule to go ahead. So timestamp ordering with Thomas Wright rule allows this transaction? No. Neither timestamp ordering nor Thomas Wright rule allows this transaction. Correct. None of the above is not there. So these two are the correct statement. Timestamp ordering protocol does not allow, timestamp protocol, and both Thomas Wright rule, both of them do not allow. Now one important point to observe over is, let's say this RA was not there. This read A was not there, right? So in that case, what would have been the read timestamp of A? Read timestamp of A would have been the last value of read, which is basically T3. And in that case, this would have been 10, right? And then when we, in that kind of situation, right, in that kind of situation, suppose this RA is not there. Suppose this RA is not there. So in that schedule, the exactly everything else will remain same, but this read timestamp A will be 10. So if this read corresponding to this read, so when I am going for this write in such a situation, then you see that according to the Thomas Wright rule, we have seen, according to the normal timestamp ordering, which will still not allow, because the this write condition will not allow. Thomas normal timestamp ordering will not allow the operation to be executed even just because of the write timestamp is greater, right? But Thomas Wright rule will say, okay, ignore the write timestamp being greater, but the read timestamp is lesser value, so I will not object. You can go ahead with the transaction, just ignore this write, do not execute this write, ignore it, ignore this write, and go ahead with the other operations in the T3 transaction, right? So now, as you can see, this question number 9 is basically that this is the same schedule, only difference is this read is not there in this schedule. As you can see, this R1A, right, R1A, that is not here, this R1A is not here. So this schedule will be basically rejected by timestamp ordering protocol, but it will be accepted by the timestamp ordering protocol with Thomas Wright condition, right? Fine. So that's it for this tutorial. I hope you guys understood what is the significance of Thomas Wright rule, how it works, and what is timestamp ordering protocol. Thomas Wright rule, by the way, why we do it? In order to increase the concurrency, right? Because if due to this write there is no such problem. If there is no read, if I ignore this write, everything else is fine. I mean, just because of this one write, which is not even affecting the schedule in any way, because read is not there. If read is there, then it is not allowed. Because read is not there, it is not affecting. Just because of this write, I am basically going for a rollback, and then again everything will have to be executed from start. So why? Just ignore this write and move ahead with the other instructions which is there in the transaction. So it increases the concurrency, reduces the time for rollback and all of that. So that's why Thomas Wright rule is a performance metric, performance improvement on timestamp ordering protocol. So that's it for this tutorial, and thank you all.